Right, yes, so hello, I am Thomas, or Tom, and I'll be presenting type-level property-based testing, which is work I did as part of my PhD with Edwin Brady. So the motivation for this work is that many systems exhibit finite state machine-like behavior, which we can model using dependent types. So these are things like, but dependent types are very difficult to get right. So how do we increase the confidence that we've gotten these types right? And quick disclaimer, I say increase confidence. This is not a proof technique. We are aiming to spot errors before we go down the deep roots of trying to write 10 lemmas to prove a thing, only to conclude we were wrong from the start. So yes, stateful systems are ubiquitous. We find them in embedded controllers for the automatic doors we walk through, ATMs. Network protocols are stateful as well. They used to be fairly simple. These days they are very complicated. So how do we go about proving that these are correct? Because it would be very nice, or not proving, sorry, testing that these are correct, because it would be very nice for them to be so. So there's sort of a spectrum of verification that one can target. There's the strongest is what we've seen with interactive theorem provers, constructive proofs, but these require, or quite often require, a lot of expertise to be able to wield. Then you have things like model checking, which lower the barrier in that you just need to know what you need to, like the properties you need to express in linear logic, and then you can push a button and off they go, but they are quite limited in their types because they exhaustively search the state space, and even then you quite rapidly hit a state explosion problem where you just cannot search the state space within reasonable time. Moving along, we then get to property-based testing, so things like quick check, where we generate random instances, and we might miss some cases, but it's hopefully stronger than unit testing, which are easy to write, but the converse being that we have to, as programmers, think of every possible case that we want to test. So, you know, we're at TyDe. Where does type-driven development fit into this? So we have dependently typed languages, which we can use to construct some advanced types, some advanced DSLs, and then the types and the type checker help us guide the implementation and verify that the implementation is correct. This so-called correct by construction approach. So if we remember or look at this Haskell function called head, takes the first element of a list, except if the list is empty, there is no first element and we get a runtime error. Converse, or instead we can use dependent types and we can index the lists by their length, which we call a vector. So now the type of head only accepts lists which are non-empty, which means it will always be safe to call it because the only things that you can call it on are things that have at least one element. So this approach sort of fits somewhere in the middle on this spectrum. So this is the example that I'm going to be using throughout. So we have this state machine of an ATM. So we start in the ready state, and then we can take the transitions which are labeled to move between our states. We can model this with some codes for the states first, and then the next thing we can model is the pin result. So you'll note that this is actually the same transition, but with different implicit or intermediary results. So when we check a pin, it's either right or wrong, so we put that in a data type, and anything that does nothing we'll just have as returning unit. So now we can define a function that states, if I get the pin right, then I move to session, and if I get it wrong, then we stay in this card inserted thing to try again, potentially. And where this really begins to shine with dependent types is that we can start constructing these monadic-like things that are indexed not only by their return type, but by the function that transitions to the next state. So in this case, you know, we have check pin doesn't change to one specific state, it changes to whatever the output of applying check pin function to the pin result was. And similarly for bind, when we get an instance of the result of the previous thing, then we need to apply the state function from it in order to know where we were and move on from there. And this is the full thing, which we call an index state monad. So why is this neat? Because now we can declare like a program that says, at the end of it, I'll return nothing, I will start in ready, and then I will finish up in ready. And the type checker helps us verify that we don't use the operations incorrectly. So we start here, we've said we'll start in ready, so we start in ready. Then we can apply the insert, because that's all we can do from a ready state, which takes us to card inserted. Then we can use check pin, because that's mostly the thing we can do in card inserted. If we get the pin correct, that moves us to session. If we get the pin wrong, then we stay in card inserted. And now we're in session, we can dispense some money, we can inject the card, and we're back in ready. It's all fine. This is helpful, although it's not totally helpful, because, so this is obviously wrong. We've said that we'll return to ready, but we never eject the card. So this doesn't type check, all good. This does. This is well typed, because we've said that we will return to ready. This says we'll return to ready. And this, indeed, if we ever get the pin correct, will move on to ready. But in this case, we just keep looping. And so we never actually do. And you might say that, you know, we can spot this with totality checking, but it's a total operation to try all 10,000 pin operations and then proceed when you find the right one. So this is clearly not how we want our ATM to behave. So this then brings me on to property-based testing, which we're going to use to spot some of this. So we've already seen some things about how this works. So we want to generate some type, and we define a function from a random integer to an instance of the type. This is called arbitrary, and we can so we say we generate arbitrary types. And then this allows us to express properties, which we test over typically 100 random inputs. So quick check has been proven to work very, very well for regular types, but how about dependent types? Well, if we consider generating an arbitrary vector, so we know how to generate the thing we want to have in the vector, but we don't know how to generate a vector itself. So we start off by generating a length, and then we generate n arbitrary elements. So far, so good. And we return that vector. Except we don't, because vect is indexed by its length, and that length in particular is nowhere to be seen, which means it's implicit. It will be given at some later state. We are trying to promise that whatever arbitrary length we generate will match exactly whatever n someone thought of at some later stage, and understandably, the type checker says no. So how do we solve this? We throw more dependent types at it, because that's always the solution. Specifically, this thing called dependent pairs, where the second thing depends on a concrete value of the first bit of the pair. So as long as we know how to generate the first bit, then we know the type of the second bit, and then we can generate that whole expression. And these little double stars desugar to dpair and make dpair as necessary. So if we go back to our vector now, when we know the length, we'll know the type of the vector. We can generate a length, we can generate another vector, and now we can put the length in here to say, I know that this length is now length, and so my vector must also have that matching length. And in fact, this is obvious enough that we don't need to state it. We can omit it, and the type checker infers the right value for that, and which saves us a lot of repetition once we've written down the type. So question is, can we do a similar thing for the ATM? With a bit of work, yes. And the details are in the paper, but essentially we can generate operations with their results, trace these, or apply these to then get a trace that we can then generate. And this is still, we're still doing quick check here, so we can control the frequency of when we generate these instances. So here we start, we have this options function which dictates which options are available to us in a given state. We've matched on the card inserted state, so we know that the only options are check pin, or we could eject the card. And in this case, we control the pin because we need to have some pin to check. We could arbitrarily generate this, but then we might hit the right pin. So we're just going to leave it as 0. And then we either fail or succeed with checking the pin. And we can apply standard quick check operators here to say that 1 in 6 times we get it right, 4 in 6 times we get it wrong, and 1 in 6 we eject it. Now, how do we apply this at the type level? This is, after all, type level property-based testing. In ITRIS2, we have this type that's called so, which is inhabited if and only if its arguments evaluate to true. So if we start putting quick check inside that, the type checker, in order to figure out whether the so type is inhabited, it will run quick check over the property. And so effectively, we're running quick check as part of our type checking process. And ITRIS2 is built on this thing called QTT, or quantitative type theory, which has erasure, which means that we can annotate the tests as erased, and then they just run at compile time and disappear from the actually compiled program. So here's one property over the ATM, which essentially says within 10 states, I will be back in ready, or I really should have gotten back to ready in at most 10 states. And if we put this in a so type, or try and run it, then the file no longer type checks. We get this error saying that when unifying so true and so quick check, we get a mismatch between true and false. So our quick check has failed. And if we examine this at the REPL, we get this trace, which says that, we can start in ready, I can insert, that's fine, and then I can just keep checking and getting the pin wrong, and within 10 states, I'm still in card inserted, which is not ready. But now that we know that there's an error, we can hopefully fix things. So we fix this by saying there's a number of retries that we have to respect in order to check the pin. If we happen to get it right on the final attempt, hooray, we can move to session. If we get it wrong, then, if we get it right, then yeah. And if we got it wrong on the final attempt, we're forced back to ready. If we get it wrong at some amount of retries, then we store 1 fewer retry in the card inserted state. And with this change, if we carry it through to the generators and our properties, then this passes and the file reloads. And if we load it at the REPL, we get this nice 100 tests passed. So this is very nice because with most verification tools, as I mentioned at the start, we have to translate between representations. So the specification, the model, and the implementation are their own things. They live independent lives, and this results in translation mistakes because we might not have the same types, or if you're using model checking, you might not have the space to search the right types, which then there's the risk that we might think we're checking the same thing, but because we have to do translation into things that approximate each other, we haven't actually verified the same semantics. By contrast, here our specification lives as part of the file and is used as part of the implementation as well, so it's the same specification everywhere. In particular, these 2 lines here. So we get this horrible thing out from arbitrary, but this state function here is exactly the states function that's in our dependent types. So we know that, and we can see here that we apply it to the result to get the next state, and this is our generating bit. So this works with the same types, the same dependent types that are being used to guide our implementation are being used to generate the traces that we specify the properties over. So I think this is really neat. And this can be generalized because index state monads, it turns out, generalize to anything that have some operations and some states that you can express in this format. That's also in the paper. So we're now testing the types, which was the goal of this whole thing. We've checked the dependent types, which help us guide the implementation. And crucially, we've not checked the implementation because it's being guided by the types. But we now have some confidence that the guidance is not misleading us, that our dependent types are not wrong, because effectively dependent types are actually type-level programs. So, we should probably be testing them rather than just applying them and going, it type checks, I guess that's fine. So if you want to talk, there's my email. The full paper is available now on the ACM. Thank you very much.
So, questions?
Thanks for the talk. I was wondering, what about shrinking? Do you do that? Is it possible with dependently typed data, and is it useful here?
That is part of the further work. So
Okay.
yes, I haven't looked into it yet, but shrinking is indeed, it would be good to have.
Right.
Yeah.
Okay.
This is really cool. It's in Idris at the moment. Can we have it in Haskell?
I will say when Haskell has dependent types, which as far as I understand
in Haskell's dependent types, would we be able to have this sort of thing?
I don't see why not, because if you can have this thing that says this type, really the key bit is just having something that's inhabited if it's true, and then you get that as part of the type checker. So yeah, I think
Nice,
that
thanks.
could be cool.
Hi, thanks for your talk. So you run these quick check tests statically, right, during type checking?
Yeah.
So where does the random seed come from? Are you allowed to generate that in Idris, or how does that work?
Yeah, that's a very good question, and a bit of a sore point at the moment. So we have type providers in Idris 2 now, so we can technically read files and try and get types. The seed is currently fixed,
Right.
and we have to fix it because the elaborator doesn't support doing arbitrary I/O. There's so there's a DSL that restricts that for type providers. So we could probably use that to add the seed at compile time, but that's not been implemented yet.
Yeah. And suppose the tests all passed, and I want to prove something about these systems. Have you looked at any kind of, or do you have any idea about how to do any LTL-style reasoning in Idris or Agda?
LTL style less so. There is some really interesting work from 2016 or 2019, I forget, by Liam O'Connor, on having this where you take a so type and then from that having a so true inhabits a proof in and of itself. And I think it could be really interesting to try and combine these things.
But the so only tells you something about one trace, and suppose you want to know something about all possible traces, right?
Yeah.
Yep.
So this would be for, it's preliminary results rather. You then go off and do the proofs.
Yeah. Okay. Thanks very much.
I also have a question. So you used quick check in the so. That means that the return type of quick check is bool. That's quite different from Haskell
that
quick
was
check.
glossing over some details. It's a maybe bool, and you have to because quick check you can run out of you can exhaust the thing and then it doesn't. You have to specify whether that is considered an accept or a fail. Is the way that I've done it, and so in the actual library that I've got, you need to say at the start whether you want that to be an accepted or not. And the trace, so the log and the trace and all of this, you only get at the REPL. You don't get as part of your type.
Okay, let's thank the speaker. And that's